Hey class and welcome back. Here's a short video going over pre-lab number 6 for you all. So here's the first question. It asks us about these two billiards balls that are going to collide with one another. One starts at rest and the other moves towards it, hits it, and then it stops as the second ball continues on. And we're asked to sketch position as a function of time for each of these. So I'm going to do this two different ways. Some of you may have made individual graphs for ball one and ball two, which is totally fine. Or you could have put them both together on the same plot, which is also fine. So again, I'm just going to show you this two different ways here. So again, the first is to draw ball one. So let's say it starts at some position we'll call 0. It's going to move at an approximately constant velocity. After some certain time, maybe we'll call it TC, it will collide, time of collision, or Todd Curtis, there you go, with the other ball. And after that point, its position will stay exactly where it was when they collided because it's no longer moving. The second ball must have started at that same initial position, right? So if we kind of follow this over, that's where it had to have started because that's where the collision occurred. Then after the same period of time, TC, the collision occurs, at which point that ball will then continue moving in the same direction ball one was moving due to the idea of conservation of momentum. So that's what those two could look like. If you were to put them on a single graph down here at the bottom, we had our, again, time of collision here. What would happen is ball two would have started at some location, again, whatever this X location is that we had the two colliding at, and we could call it XC or something. So it would have started at that XC value and it would have stayed there until the collision. During that first time before the collision, ball one would have been moving towards it. They would have eventually collided, after which point ball one stayed in that same location where ball two originally was, and ball two would continue off in a straight line, looking something like this. So that's what your pre-lab question 1A should look like, either, again, separate graphs or one combined graph, either way. I think the combined graph really helps visualize even better what's going on, but I think they both work well. Then if we kind of create some new space for us, question 1B asks us to make conclusions about conservation of momentum. So what can we say about conservation of momentum in this case? Well, what I would say is if the net external forces, so if the net external forces, not internal, right? There's some force between the two balls as they collide, but if there's no other net external forces, if that's equal to 0, then we can conclude that momentum is conserved. So the total momentum of our system, the two balls together, is conserved initial to final. So that's the idea of conservation of momentum, is if the net external forces are 0, then you have conservation of momentum, which means that the initial momentum of ball one must be equal to the final momentum of ball two, because we know the initial momentum of ball two is 0 since it's not moving, and we know the final momentum of ball one is also going to be equal to 0 because it's not moving after the fact. So that's what I would say for pre-lab question number 1. For pre-lab question number 2 now, it asks us to write down the total momentum of a two-marble system, assuming both marbles have the same mass m and are both moving at the same velocity v. So again, if we wanted to do the total momentum, normally it would be m1 v1 plus m2 v2, right? For, again, the two different balls in our system. But in this case, since they have the same mass and same velocity, it would just be mv plus mv. And so our momentum, my arrows are not going beautifully here, would just be mass times velocity times 2, because we have two different balls. Similarly, we're asked to do the same thing for kinetic energy. So again, for the kinetic energy, it normally would be 1/2 m1 v1 squared plus 1/2 m2 v2 squared. But since they're both the same mass and velocity, we just end up with 1/2 m v squared plus 1/2 m v squared. And adding those together, the total kinetic energy just comes out to mv squared. And that's our total kinetic energy, and that's our total momentum of the system for question number 2. And then the last question, question number 3, asks us about Newton's cradle. So if you've ever played with one of these, it's a fun toy. I always like playing around with it. I actually have one in my office and one in our physics lab. But But if you pull up one ball, it's going to hit and exactly one ball will bounce up on the other side. If you pull up two, it will hit and two will bounce off the other side, leaving three behind. If you pull up three, leaving just two behind and let it hit, three will move up on the other side. So the two that were stationary will go and the middle one will continue to move. And so you have this constant going back and forth. Now, if you think about just the idea of conservation of momentum, you would think that if you had two balls, you'd have m times v plus m times v, you'd have 2mv, just like we had up here, of momentum, right? And so then it thinks like, why can't they swing down, hit, and just send one off at double the velocity? Because by conservation of momentum, 2mv would still become 2mv, and that seems like it could make sense. But the reason this is impossible is by analyzing the idea of energy. So it says as a hint, just to make your life easier, assume that you have a perfectly elastic collision. So again, for any collision that is isolated, again, if the net external force is zero, then you're going to have conservation of momentum. But you only have conservation of kinetic energy if it is elastic. And so usually you either have to be able to calculate to prove that, or you need to be told that it's elastic. So to kind of help us analyze this situation, if we think about before and after this collision, let's compare, as the problem asks us to do, the kinetic energy. So our kinetic energy initial, we would have two balls, each going 1/2 mv squared. So it looks just like what we did in the previous question. So our initial kinetic energy would just be mv squared. But the kinetic energy after, if we sent off one ball at double the speed, would just be 1/2 m times 2v quantity squared. And 2v squared is 4v squared, right? 2v quantity squared, the 2 gets squared and the v gets squared. So you end up with 1/2 m times 4v squared. And so your kinetic energy becomes 4 times 1/2 is 2 mv squared. So if you were to shoot one off at twice the speed, even though momentum would be conserved, you would double the energy and you magically created energy out of nowhere, which is impossible. And so that's why, by the idea of energy, you could never shoot off one at double the speed, even though it makes sense in terms of momentum. It would be impossible in terms of energy because you can't create energy from nowhere. So that wraps up the video for pre-lab number 6. I hope you guys have a boy howdy fun time with this lab. And keep in mind, right, momentum will be conserved anytime you have an isolated system, but kinetic energy is pretty much always lost unless you have the specific scenario of what we call a perfectly elastic collision, which is pretty rare in day-to-day life, but there are scenarios that we can approximate as nearly elastic as well. So anyway, have fun with the lab. Let me know if you have any questions. Have a box-worthy day.